Welcome to our deep dive all about black holes. You've put together quite the collection of articles and videos and research notes, so looks like you're ready to really get into this, huh?
Definitely. It's going to be fascinating to explore how our understanding of black holes has changed, from being seen as just these mathematical quirks from Einstein's theory of relativity to now.
Yeah, to now being recognized as these real physical objects that actually shape our universe.
Yeah, exactly. And with the help of the James Webb Space Telescope, we are making just groundbreaking revelations.
It's pretty amazing.
Yeah, it all started really with Einstein's theory of relativity.
Okay.
And you see, most people find the idea of space-time mind-bending, but it was the physicist Carl Schwarzschild who, during World War I, he found a solution to Einstein's equations that predicted a point of no return,
Oh, wow.
a region of space where gravity is so strong that nothing, not even light, can escape. And we call this
The event horizon.
exactly the event horizon.
It's kind of poetic, isn't it, that amidst the chaos of war, Schwarzschild unveiling this profound cosmic concept?
Yeah, it really is.
What I find so fascinating is that this prediction, it's stayed shrouded in skepticism for decades.
Oh, yeah, for sure. Many physicists just couldn't wrap their heads around an object so dense that it could warp space-time to that extent.
Yeah, that's wild. So when did things start to change?
Well, the turning point really came with the rise of observational astronomy.
Okay.
As technology improved, astronomers began observing phenomena that just defied conventional stellar physics.
So are you saying these observations were like breadcrumbs leading to this big cosmic mystery?
Exactly. One very important discovery was Cygnus X1.
Okay.
It's a powerful X-ray source in the constellation Cygnus.
Oh, wow.
And what astronomers found was a visible star orbiting an invisible companion object.
Okay.
And this companion was extremely massive but compact and was emitting X-rays, which is a huge sign of intense gravitational activity.
So they couldn't actually see this object, but the evidence pointed to something massive and dense just pulling the strings.
Exactly. And after analyzing Cygnus X1's properties, like its mass and the behavior of its visible companion, the scientific community started to accept that this invisible object was, in fact, a black hole.
Wow.
Yeah, it was a major shift.
It was a paradigm shift.
It was. It really confirmed that they exist, and it revolutionized our whole understanding of stellar evolution.
This is where it gets really interesting for me now that we know black holes exist.
Yeah.
You mentioned that there are different types of black holes.
Yes.
What's going on there?
So think of it as a cosmic zoo of black holes.
Okay, I like that.
So we have stellar mass black holes, which are born from the death throes of massive stars.
Okay.
These are relatively small but very dense.
Okay.
And then we have supermassive black holes.
Oh, yeah.
Yeah, which are lurking at the hearts of galaxies, including our own Milky Way.
Wow.
And these behemoths can hold the mass of millions, even billions of suns.
Millions of suns in one spot. That's just mind-blowing. So, okay, I'm trying to wrap my head around all this.
Okay.
If we could, journey toward a black hole, what would we experience?
Buckle up.
Okay.
So approaching a black hole, the first thing you would see is gravitational lensing. So the intense gravity is warping the fabric of space-time. It's bending the light from distant stars.
Okay.
So you'd see stars smeared into rings and arcs around the black hole.
So it'd be like a cosmic kaleidoscope.
Exactly.
That's incredible. And would time be affected as well? I've heard about time dilation near black holes.
Yeah, absolutely. Time would slow down drastically for you compared to someone who is further away.
Really?
Yeah, it's like a natural time machine.
Whoa.
Imagine looking back at Earth for near the event horizon. You would see events unfolding at a fast pace while you are in slow motion.
Whoa. That's like time travel in reverse.
Yeah.
But what about the event horizon itself? What happens when we cross that point of no return?
Well, that is the ultimate mystery.
Right.
Yeah, classical physics suggests anything falling into a black hole is gone forever, crushed into an infinitely dense point at the center.
So the singularity.
Yes, the singularity.
Okay, wait. But wouldn't that contradict quantum mechanics, which states that information can't be destroyed?
Right.
That's where it gets mind-boggling for me.
Yeah, you've stumbled upon one of the biggest puzzles in modern physics, and we call it the black hole information paradox.
Okay.
So general relativity suggests information is lost inside a black hole, while quantum mechanics says it can't be destroyed.
So two fundamental theories are at odds.
Yeah.
How do physicists reconcile this?
That's the million-dollar question.
Yeah.
One promising development involves Hawking radiation, a concept proposed by Stephen Hawking.
Yeah.
He theorized that because of quantum effects near the event horizon, black holes actually emit a faint thermal radiation.
So black holes aren't completely black,
Yep.
then they leak information back into the universe.
That's the idea. Hawking radiation could carry information about what fell in, although it would be scrambled.
Okay.
So this could offer a way to preserve information and resolve the paradox.
Wow, so even though we can't see inside a black hole, Hawking radiation might be giving us like little glimpses of what's happening beyond the event horizon.
Exactly.
This is all so fascinating.
It's an active area of research, and it's pushing the boundaries of theoretical physics and how we understand reality itself.
We've covered a lot of the basics here, the journey from skepticism to confirmation.
Yes.
And even touched on those mind-bending paradoxes.
Yes.
And it's so clear that these black holes are more than just points of no return.
Right.
They're like windows into the deepest mysteries of the universe.
And with the advent of powerful telescopes like the James Webb Space Telescope, we're on the verge of unraveling even more secrets about these enigmatic objects. In fact, let's shift our focus now to supermassive black holes residing at the centers of galaxies.
Okay, bring on the Titans. Before we get lost in the vastness of supermassive black holes, what questions do you have for us so far? What stands out to you most from what we've talked about so far?
Welcome back.
All right, so we're back and ready to dive into those supermassive black holes.
Yeah, these supermassive black holes are mind-boggling just in terms of their scale.
They are.
Imagine like millions or even billions of suns crammed into a single point.
It's just hard to wrap your head around that much matter in one place.
It really challenges our understanding of size and density.
It does. And what's even more puzzling is how these behemoths formed in the first place. Like, they didn't just appear out of nowhere, right?
Definitely not. The mystery of how they form is a captivating one.
Yeah.
One prevailing theory is that they originated from giant gas clouds in the early universe.
Okay.
And these clouds were composed mostly of hydrogen and helium.
Okay.
And they had masses exceeding millions of stars, so they had the potential to collapse and form truly gigantic stars.
So stars so massive they would dwarf our entire solar system.
Exactly.
It's hard to even imagine.
I know, right? And as these supermassive stars use up all their nuclear fuel, their cores can collapse catastrophically, giving birth to black holes significantly larger than those formed from typical stellar collapses.
So these ancient supermassive stars were kind of like seeds for the supermassive black holes we see today.
Yeah, it's like cosmic evolution on a grand scale.
Yeah, exactly.
But there's another intriguing possibility.
Oh.
Direct collapse.
Okay.
So picture this. A massive gas cloud in the early universe completely skips the star formation stage
Oh, wow.
and collapses directly into a black hole.
Whoa.
This would create a black hole with a huge starting mass right from the beginning.
So it's like skipping a step in the cosmic recipe for black hole creation.
Yeah, exactly.
But wouldn't that require some incredibly extreme conditions in the early universe for that to happen?
You're exactly right. Direct collapse would need a very specific set of circumstances.
Yeah.
And this scenario could explain how supermassive black holes formed so rapidly in the early universe, which is a puzzle we've been trying to solve.
So it helps us make sense of the timeline.
Exactly.
Because we see these distant quasars, and those are incredibly luminous, distant objects that are powered by, you guessed it, supermassive black holes.
That's right.
It's like they're beacons from the early universe.
Exactly. Quasars emit huge amounts of energy, and it's thought to be generated as matter spirals into the supermassive black holes at their cores.
Okay, so by studying these quasars, we're basically like looking back in time, witnessing the growth of supermassive black holes in the early universe.
You got it.
It's like having a time machine. But if these quasars are signaling early supermassive black holes, how could they have grown so massive so quickly? There has to be some sort of limit to how fast a black hole can devour matter.
Right. You're hitting on a crucial point.
Okay.
There's this theoretical limit called the Eddington limit. And it basically describes the balance between the pull of gravity inwards and the outward pressure from radiation that's emitted by the hot gas falling into a black hole.
So it's like a cosmic speed bump that prevents black holes from gobbling up matter too quickly.
Exactly. However, if supermassive black holes formed through direct collapse, they'd start off with a huge mass advantage.
I would guess.
And this would let them overcome the Eddington limit and grow much faster.
So it kind of like solves for that early formation and rapid growth.
Exactly. It could potentially resolve that puzzle.
Direct collapse, huh? It's a pretty elegant solution, But is there like any observational support for it? Does the James Webb Space Telescope come into play here?
You know it. The James Webb, with its amazing infrared vision and sensitivity, is revolutionizing how we understand the early universe.
I've seen some of those images, and they are incredible.
They're amazing.
So is it finding evidence for direct collapse?
Well, its observations have shown us galaxies that are far more massive and structured than we thought possible at such early times.
Really?
Yeah, and this discovery really challenges our previous models of galaxy formation and suggests that supermassive black holes might have played a bigger role than we originally thought.
So these early supermassive black holes could have been like architects shaping the evolution of galaxies.
Precisely. Their immense gravity can actually control the movement of stars and gas within their host galaxies,
Oh, wow.
influencing their structure and how they evolve over time.
It's like this cosmic ballet with the supermassive black hole leading the dance.
I love that analogy.
So what other insights has the James Webb provided about black holes?
Well, besides looking into the distant past, it's also giving us amazing views of black hole environments that are closer to home.
Oh, cool.
Yeah, it's capturing images of these swirling disks of gas and dust around supermassive black holes, and we call these accretion disks.
Okay.
And these images are revealing intricate details about their structure and how they move.
I've seen some of those pictures, and they're mesmerizing.
They really are.
It's like we're getting a front row seat to how these supermassive black holes interact with their surrounding.
Exactly. And the James Webb isn't just about taking pretty pictures.
Right.
It's gathering important data that will help us answer fundamental questions about black hole physics.
Okay.
By studying the light emitted from matter spiraling into a black hole, we can actually test Einstein's theory of general relativity in these extreme gravitational environments.
That's incredible.
It's like having a front row seat to the universe's most extreme physics experiment.
Yeah, exactly.
Yeah.
But we can't ignore the biggest mystery of, right, like what lies beyond the event horizon?
Right.
Like what happens to matter that falls into a black hole?
Well, that's still one of the biggest mysteries in science.
For sure.
We know that going past the event horizon is a one-way trip.
Yeah.
No information can get out from inside a black hole. So any insights we have about what's going on in there are based on theoretical models and what we know about physics.
So we're venturing into uncharted territory using theoretical principles as our guide.
Yeah, it's pretty exciting.
It is.
Classical physics, specifically general relativity, suggests that matter falling into a black hole will collapse into the singularity,
Right.
which is that point of infinite density at the center.
Okay.
However, recent advances in theoretical physics are suggesting that quantum mechanics might actually change this classical picture.
Really? So quantum mechanics might prevent the singularity from being a point of infinite density.
That's what's so intriguing. Some theories propose that instead of just a point, the singularity might be a more complex and dynamic structure,
Okay.
possibly governed by laws of quantum gravity that we don't even understand yet.
So the singularity might not be an end point, but rather like a gateway to something even more complex.
Exactly.
Potentially something even more bizarre than we can imagine right now.
Precisely. Some theories even go as far as to explore the possibility of wormholes.
Whoa, wormholes.
Yeah.
Those are like hypothetical tunnels through space-time that could connect a black hole to another part of the universe.
Right, or even to another universe entirely.
That's a concept that really captures the imagination. It's like a cosmic shortcut.
Yeah, it is. And while wormholes are still purely theoretical, they really highlight the mind-blowing possibilities that come up when we try to combine general relativity with quantum mechanics.
That's amazing.
Black holes, with their crazy gravity and mysterious nature, are at the forefront of this scientific exploration.
Yeah.
They're pushing us to rethink our understanding of space-time and gravity.
It sounds like we're on the cusp of a brand new era in physics,
I think so, too.
where our understanding of the universe might be totally transformed.
Absolutely.
And black holes are leading the way.
They're like cosmic laboratories that allow us to test our theories in the most extreme environments we can imagine.
Yeah, it's really incredible. But before we get too carried away with all this speculation,
Right.
let's take a step back and just appreciate how far we've come in understanding black holes.
Yeah.
You know, from their theoretical prediction to actually observing them and now exploring all of their amazing properties.
It's really a testament to human curiosity
It is.
and the collaborative spirit of scientific inquiry.
Absolutely. But like with any scientific endeavor,
Yeah.
for every answer we find, we just end up with more questions.
Right.
Like the mystery of how those supermassive black holes formed in the early universe is still so intriguing.
It really is.
Like, how did they get so big so fast?
Right.
And what about the information paradox? It feels like we're grappling with this fundamental conflict between general relativity and quantum mechanics.
Yeah.
Does information really disappear inside a black hole? Or is it preserved in some way, maybe through Hawking radiation?
It's a big question.
These are such profound questions, and they're driving cutting-edge research in theoretical physics. You know,
They really are.
we're having to confront the limits of our current understanding of gravity and quantum mechanics.
Yeah.
And this could potentially pave the way for a whole new revolution in how we understand the universe.
It's an exciting time to be studying physics.
Black holes are no longer just these theoretical curiosities,
Yeah.
they're real objects.
They are.
And they have this huge impact on how galaxies evolve
Right.
and potentially even the fate of the universe itself.
Exactly.
Remember those quasars we talked about?
I did.
They're shining so brightly from the early universe,
Yes.
powered by those supermassive black holes, just devouring matter at incredible speeds.
Yes. It's amazing.
They're a real testament to how dynamic the universe is,
They are.
and to the incredibly powerful forces that are at play.
Absolutely. And don't forget about those jets of particles and radiation.
Oh, yeah, those are awesome.
Yeah, they're launched from the poles of black holes.
Yeah.
And they can extend for thousands of light years,
Wow.
influencing the interstellar medium and potentially even triggering the formation of new stars in distant regions.
It's just this grand cosmic dance,
Mm,
between gravity, matter,
Yes.
and energy,
it is.
with black holes playing a leading role.
They really are the stars of the show.
We've covered so much ground in this deep dive.
We have.
We've explored the life cycles of stars, the mysteries of gravity, and those mind-boggling paradoxes that come up when we try to understand what's happening inside a black hole.
Yeah.
It's clear, though, that our journey is far from over.
Oh, definitely not.
Black holes were once considered these cosmic oddities,
Yeah.
but now they've become so central to how we understand the universe.
They really have.
And they remind us that the universe is full of surprises, and there's still so much we don't know.
There's always something new to discover.
But with every new observation and theoretical breakthrough,
Yeah,
we're getting closer to unlocking their secrets and unraveling the mysteries of the cosmos.
we are.
What stands out to you most from everything we've explored? What new questions have come up in your mind?
As we wrap up this deep dive, I want to leave you with a final thought-provoking question.
Sure.
If our universe did begin with a singularity, much like a giant black hole, what does that mean for the concept of before the Big Bang? Could there be a reality beyond the event horizon of our universe?
That's a question that really pushes us to think about the nature of reality itself,
It does.
the boundaries of our knowledge,
Yeah.
and the infinite possibilities that are hidden within the vast expanse of the cosmos.
It's a beautiful and mysterious universe out there.
It really is. And on that note, we invite you to keep exploring, keep questioning, and never lose that sense of wonder as you look up at the night sky.
Keep looking up.
The universe is this vast and mysterious place, and we've only just started to uncover its secrets. Wow, it's amazing how much we've learned about black holes in this deep dive.
It's really remarkable, isn't it?
It is. We've gone from their theoretical beginnings to actually seeing them
Yeah.
and exploring all these different types, and even grappling with those mind-bending paradoxes they create.
Those paradoxes are really something else.
They are. But as with any scientific journey, it seems like every answer we find just leads to even more questions.
Absolutely. It's like peeling back layers of an onion.
Exactly.
Yeah.
Like the formation of those supermassive black holes in the early universe still has me scratching my head.
Yeah, that's a big one.
How did they get so incredibly massive so quickly?
Right. And the James Webb Space Telescope, with its observations, has just made the mystery even deeper,
It really has.
revealing these galaxies that are much more mature than we expected to see in the early universe.
It's almost like the universe had a head start that we just weren't aware of.
Yeah, it's challenging our current models for sure.
It is. And let's not forget about the information paradox.
Oh, right, the information paradox.
It's like we're stuck in this battle between general relativity and quantum mechanics.
Yeah, two of the biggest theories in physics.
Like, does information truly disappear forever inside a black hole?
Right?
Or is it preserved somehow, maybe through that Hawking radiation we talked about?
That's a question that's keeping a lot of physicists up at night.
It really is. These are some seriously profound questions.
They are.
And they're driving some incredible research in theoretical physics.
Pushing the boundaries of what we know.
Exactly. And black holes, they're not just these theoretical ideas anymore.
No, they're not.
They're real objects
Uh-huh.
with a huge impact on how galaxies evolve.
Yeah.
And maybe even the fate of the entire universe.
It's Mind-blowing to think about.
It is. And those quasars we discussed
I
earlier,
remember those.
they're shining so brightly from the early universe,
Yes.
fueled by those supermassive black holes just gobbling up matter at incredible speeds.
They're like cosmic feasts.
They are. They're a true testament to just how dynamic and powerful our universe really is.
Absolutely. And let's not forget about those incredible jets of particles and radiation shooting out from the poles of black hole,
Oh, yeah. Those are amazing.
extending for thousands of light years.
That's incredible.
Yeah, influencing the space between stars and possibly even helping to kickstart the formation of new stars in faraway regions.
It's like this epic cosmic dance,
It really is.
with gravity, matter, and energy all intertwined,
All taking their turns on the cosmic dance floor.
and black holes leading the way.
Definitely the stars of the show.
We've come a long way in this deep dive.
We have.
We've learned about the life cycles of stars,
Yeah.
the mysteries of gravity,
Uh-huh.
and all those paradoxes that come up when we try to wrap our heads around what happens inside a black hole.
It's been quite a journey.
It has. And it's clear that our journey of discovery with black holes is far from over.
Oh, it's only just begun.
Exactly. They were once seen as these weird cosmic oddities, but now they're crucial to understanding the universe as a whole.
They really are at the heart of it all.
They really are. And they remind us that the universe is full of surprises.
Always keeping us on our toes.
And that there's still so much out there that we just don't know.
It's humbling and exciting at the same time.
It is. But with every new observation
Yes.
and every new theoretical breakthrough,
Uh-huh.
we're getting closer to unlocking their secrets
Peeling back the layers of the cosmic onion.
and revealing the true mysteries of the cosmos.
It's an incredible time to be exploring the universe.
It really is. And on that note, I want to invite you all to keep exploring,
Yes, keep that curiosity alive.
keep questioning, and never lose that sense of wonder that we all have when we look up at the night sky.
Keep looking up and asking why.
Because the universe is a vast and mysterious place,
It is.
and we're just beginning to uncover its secrets.